So previous class we will discuss that work done for different processes like isothermal reversible process. So we are left with adiabatic reversible process, right? So now we are going to discuss that work done for a reversible adiabatic process or adiabatic reversible process. So we are left with a reversible adiabatic process. So what is it for reversible? Reversible means P external equal to P internal equal to P gas, that not equal to constant. So we have already discussed that for reversible processes, what we are saying that P external is equal to P internal plus delta P, and this value is very small. So we assume that P external is nearly equal to P internal, and P internal that is equal to P gas. So P internal means pressure per systems, and suppose if a system is gas, then P gas. So these are the conditions for reversible processes. We have already discussed in the past lecture. So for reversible processes means P external equal to nearly equal to P internal, nearly equal to P gas, and that is not equal to constant. And for adiabatic process, dq equal to 0, that is no heat is transfer. So we are studying the work done if the process is reversible and adiabatic. So if both the conditions, if we apply to work done, then what will be the work done? So now we are deriving the work done for reversible adiabatic processes. Means these conditions and these conditions we will apply in work done expression. So work is minus P external delta B. Yes, this is the work done expression. So if says for reversible, then P external is not constant. So for reversible, this is P external T. So P external is not constant for reversible process. That's why you use these expressions double equal to minus P external dB, where P external, P external equal to P internal equal to P gas, not constant for reversible process. So what we will do, like for isothermal process, what we were doing, the Pb equal to nRT. Since T equal to constant for isothermal, so we used to do Pb equal to nRT, and since T constant, N constant and R constant, so what we used to do, P1 B1 equal to P2 B2 equal to constant. So we were assuming like that for isothermal process. But for adiabatic process, the problems arise is Pb equal to nRT. If I apply the ideal gas equations, all these terms Pb and Pbt all are changing, because for isothermal, that's why that was T was constant. So you says that Pb equal to nRT, where this nRT is constant, so P1 B1 equal to P2 B2 equal to constant, we says. But for adiabatic process, since here only Q is equal to 0, but Q is not here in the ideal gas equation, so here what, P1 B1 and T1 equal to nR, or if I search PB T equal to constant equal to NR, means this NR, this value is constant. Say number of one n equal to 1 moles, that is constant. That is like numbers, so that is constant. R is a gas constant, so PBT equal to constant. So I can say P1 B1 T1 equal to T2 B2 equal to T2 equal to NR. So this is constant, so I can write here constant. But the problem is, unlike ideal gas, we have to put only two values were changing, P1 P or B. But here the three values are changing, P, B and T. So we need to know the three values. So it is not possible to in exam they are giving the three values P, B, T. So it is not a possible. So they will not give three values. So for that case, for adiabatic process, we will not go like we are going for reversible adiabatic reversible isothermal process. We used to use the formula of ideal gas, and used to say that Pb equal to nRT, and since T is constant, so Pb is constant, so we used to put P1 B1 equal to P2 B2, and we used to put in the work expressions. But here, since three terms are changing, so we cannot put this values. So what is do for that, we have to take that, like in the after this class we are going to discuss that first law of thermodynamics. What it says that delta U, that is internal energy, equal to delta Q plus delta W. And what he says, since for adiabatic process Q equal to 0, so delta Q is 0. For adiabatic process this is 0, so we can put that delta U equal to delta W. And what he says, and we have already discussed that delta U equal to NCB delta T. We have already discussed that. Sorry, sir, this value also we will discuss after our first law of thermodynamics. So delta U equal to NCB delta T. So this one also we will discuss after we study the first law of thermodynamics. So delta U equal to NCB delta T. And work expressions we know, that is minus P dB. This is the work expressions, P external. So let me just put this value. So what I will put, that minus P dB equal to delta U value is NCB delta T. I just put that this value, delta U value is this, and delta W value is this. So I just put, this is equation 1. So I put that, I just put A and B in equation 1. So I get this value. So now what I will do, sorry. So now I will use the ideal gas equations. So ideal gas equation, what says Pb equal to nRT. So I just want to put the okay. After that, then P equal to nRT by B. Okay. So I want to put that value of P over here, because this is for reversible. P external is not constant, so it is in integration. So I want to put the value of P here. So what the value will be, nRT by V dV equal to NCB delta T. Yes. So what I'll do, this NR is constant. So NR T by B dV equal to NCV dt, and this n will cancel, so that will be minus R T by B dV equal to Cv dt, and I will take this T here, then what will it will be? So what I will do, minus R dV by B, and I am taking this T value over here, then Cv dt by T. Cv is constant, so if I do the integrations, then dV by B is log E, so minus R log E B, and suppose this is from B1 to B2, then this is B1 B2. Similarly Cb, and this is T1 to T2, then T1 to T2. So what I will do, sorry, this log value will come, right? So Cb log E T1 to T2. So what I will do, then this will be minus R log E B2 minus log E B1. This will be Cb, this will be log E T2 minus log E T1. Okay, so what we will do, we know that log E B2 log E A minus log E B, then this is equal to log E B by A, log formula. So I will use here, so minus R, this will be log E, sorry, this will be A by B, right? A by B, so this will be B2 by B1, and this will be equal to log E T2 by T1, and here Cb is there, and another also we know that log E x square, then this power can be taken into here coefficient, that will 2 log E x. Yes, this 2 can be taken here, so this 2 I can take here, so that's what I am going to do here. So log E B2 by B1, so this one will be taken here, because this one I can take here, because we are taking here, so you can move here, so that's why I'm moving this value, this minus R to here, so this is minus R log E T2 by T1. I will put here Cb. So what I will do, so we also know that if B2 by B1 minus 1, then this we can put by B1 into B2 1, so just reciprocal I can do it here, so that's why what I do, this is the log E, that one I can write B1 B2 R, I just do the reciprocal, so minus R will cancel it, convert to plus R, then this one again I can write log A, this is same, I will put Cb, so both side log A is there, so I can cancel it. So what I get, B1 B2 R equal to T2 by T1, Cb I got, then just do the cross multiplication. So what will be that, or we can write for simplification, so you can do what, this means B1R, so that was the whole term written, so I'm writing individually. B2R, this is T2CB, this one I'm writing T1CB. So now do the cross multiplication. So previously it was whole, so I taking individually. Then what happened, do the cross multiplications here, this, so B1R, and that is T1CB. Similarly B2R, that is T2CB. Okay, so temperature we not need, so what we will do, again we will put PB equal to nRT, ideal gas formula. So this is happening, this is for ideal gas equation. We are doing the reversible additive process for ideal gas equations, so that's why we are using the ideal gas formula repeatedly. So PB equal to nRT, so here nRT equal to PB, so I can say that T equal to PB nR. So I will put this T value here. Then what happened, B1R, and T1 is this value I'm putting, so PB, let me put, so P1CB, P1CB nR CB. Okay, so similarly for T2 I can put this value I'm putting here. So again I will put T2, this value PB nR2. So since this is 2 is here, so I can put that P2, and T2 is CB, and B2 CB, and B2R, that is nR whole will be by CB, right? So this again CB. So what I got, so this value and this value can cancel because both side nR to the power CB and nR to the power CB, so I can cancel it. So this what I get, B1R P1CB B1CB equal to P2CB B2CB B2R. So what I do is both that P1 B1 is there, so I want to multiply it, because we know that AM into AN equal to AM plus N. So I use this formula here. Then what happened, B1, so both are B1 B1, so this will add R plus CB, and then P1 CB. Similarly here also P2 CB and B2 CB plus R. Okay, so this one I use. So what I'll do, so both side I added, then what I do, since we know that Cp minus Cb equal to R, this we know, so I want the gamma value, because we want to say that gamma here we are going to use, so I need the gamma value. So what I'll do, I will divide this to Cp Cb, so Cp minus Cb equal to gamma, so I want the gamma value here. So what I'll do, divide Cp equal to gamma. So what I says, divide Cb both sides. So here if I divide Cb both sides, then I will get the gamma. So Cb is there, so if I divide by Cb, here also Cb, this is R, again here Cb, then what I get here, this is gamma, Cp by Cb is gamma, and this is 1, and this is R by Cb. then I want to get the value, because here CB is there, so I want the value CB equal to R gamma minus 1. So I want to put this value CB equal to R gamma minus 1, I want to put here. So what I'll do, I just you put this value here, so I'm going to just erase it. What you get, CB equal to R gamma minus 1. So I'm just going to use this CB here. So B1 R CB, I'm going to put this value R gamma minus 1. Similarly, P1 CB value I'm putting here R gamma minus 1. Similarly, for P2 CB value I'm putting this, that is R gamma minus 1, and here again I'm going to put this value. So I'm writing here so B2 CB value is R gamma minus 1 plus R. So I just want to add this value, then what we get, B1. So denominator gamma minus 1, so it will become R gamma minus 1 plus R gamma minus 1. Similar for P1 is R gamma minus 1. Similarly for P2 is R gamma minus 1 and B2 is R minus 1 plus R. Yes. So what the value will get, B1, this will be R gamma minus R plus R equal to gamma minus 1. P1 is R 1, P2 is R 1 and B2 is R gamma minus R plus R gamma minus 1. Okay, so I just add it, and what this cancel, here also this cancel. So what value we get, B1 R gamma by gamma minus 1, P1 is R gamma minus 1 and P2 is R gamma minus 1 and B2 is R gamma minus 1. So this value we get, and if I take that both sides, that R gamma minus 1 is there, here also R gamma minus 1 is there. So what I'll do, that let's say B1 R plus P1, this is gamma R gamma minus 1. Okay, yes, everything is right. R gamma minus 1. Okay, R cancel. Okay, okay. So I'm taking here gamma common, then this will become what, R gamma minus 1, because here also R gamma minus 1 is there, here also R gamma minus 1 is there, so I'm taking R gamma minus 1 as common. And similarly for here P2 here and B2 gamma, taking R gamma minus 1, so both side this is there, so I can cancel it. So what you get, sorry, this is not in multiplied, this is in multiplied, right? Because this is already in multiplied. So P1 B1 gamma equal to P2 B2 gamma. So this is the Poisson's equations. Poisson's equations. So if we not derive this whole equation, then if you remember this value also, it's fine. Like P1 B1 gamma P2 B2 gamma equal to constant. If you remember this value also, it is fine. So if you derive, then also fine. If you're not able to derive, and if you remember only this value, then also it's fine. So basically why you calculate this value? Because for reversible adiabatic process, three variables are there. So three variables, if you get in the exam, it is not possible. If two variables like isothermal, so on that case we are not doing this one. So since three variables, three values are changing, so that's why we need to calculate this P1 B1 equal to gamma, P2 B2 equal to gamma equal to constant. Because if he says P1 B1 T1 equal to P2 B2 T2 equal to constant, on that case we are requiring the three variables, and three values if we change, then it is not possible to calculate. It will become very tough. So we want two values like I did isothermal cases. So for that, just we have to do P1 B1 gamma. This is for this is for this is for adiabatic reversible process. So we have calculated that by taking dq constant for adiabatic, and we have calculated this value. So now what we will do, we put this value to our equation. What we say that work, we are going to calculate work, right? So that is P external delta P. So we get the problem at where we for doing P external, because this is for reversible, this is not constant, so we want to do integration. So but we are not getting that value, like P B equal to nRT, so T is not constant here, so we were facing the problems how to do integrations of P external. So we are not able to take the ideal gas equations because three terms, three values were changing. So that's why we calculate the Poisson's equations. So now what I will do, we will do that P1 B1 gamma equal to P2 B2 gamma equal to constant. So what I say that P1 gamma equal to constant, let's say it's K. Okay, so or we can say PB gamma equal to K. So if I want the P, then what I'll do, P equal to K B gamma. So I want to put this P value here, then what you get, W equal to P external, sorry. So I'm taking the P external value here. See, I'm using the PB, this is the ideal gas equations, and I already said that P external nearly equal to P internal and nearly equal to P gas. So I can take any value for reversible cases, because very small changes it happened. And what I said that P external equal to P internal plus dB, and this value is very small, so we are taking that P external nearly equal to P internal, and that is equal to P gas. So that's why I'm taking P external. I'm taking the directly from ideal gas equation. So I can put this P external equal to K B by gamma. So I can put this value here, K B gamma dB. So what do here, W equal to this, so K is constant, so this, then what I put this value, if I take above, then this will be negative B minus gamma dB. Then what you do, so integrations, so we know what the integration, so it's negative, then we know that integrations of x square, suppose xn, then this will be what, xn plus 1 and n plus 1, and if it is x minus n, then it will be x minus n plus 1 minus n plus 1. So here this is same like gamma b minus gamma to the power minus gamma. So what I'll do, this will be what, so okay, b minus gamma plus 1, and here n minus 1, that is minus gamma plus 1. This is the value. We have to do integrations like this. So I did the same formula here. So what I will do now, so if you do the integration, then we are getting right. So w equal to, so I want to take this value here, so here negative, so what will its value become, gamma minus 1. So if you take the negative here, then k negative, k will get positive, and gamma minus 1. So basically minus k into what is there, minus gamma plus 1. Then what is it, I take the negative here, k gamma minus 1. So if we multiply with this, then we get this value. Okay, so this value has came right this, then this is b minus gamma plus 1 and gamma minus 1. Then what will do, and this is from b1 to b2. Okay, b1 to b1. So k gamma minus 1, so I will put the value, I take this value here, so that came here, right? Yes. So I can put b2 minus gamma plus 1 minus b1 minus gamma plus 1. This is the value. Okay, so w become k gamma minus 1. So this value will be how much? So this value we can write b2 minus gamma b1 1, and so this is b2 1 and b1 minus gamma and b1, because a x plus y, then this is became how, ax plus, sorry, ax ay, so ax into ay, then this is equal to ax plus y. So thus I want to separate it, then this has came. So now what we'll do, that k, and k value where you get, k equal to, we say that Poisson's equations, b1 gamma equal to b2 gamma equal to constant we say. So this constant I take here as k, so I can put the value k, this value again here, so I can put. So first what you will do, just multiply k with all these things. So this is k b2 minus gamma b1 and k b1 minus gamma b1. So to put the value k here, so w equal to k is, for b2 I can put p2 b2, so p2 b2 gamma and b2 gamma, this is, sorry, this is b2 and b2 minus k again I put here. So p1 b1 gamma b1 minus gamma b1. So what you get here, this cancel, this cancel, because ax and a minus x, this what, a x minus x, that is 0. So a0 equal to 1. So that's why I cancel it. So w equal to p2 b2, this is, so this is near downside, gamma minus 1 is there, gamma minus 1. So w equal to, so this cancels, so p2 b2 minus p1 b1 gamma minus 1. And again you use the ideal gas equation, P equal to nRT, or p1 b1 equal to p2 b2 equal to nRT. So this one is we know, but also nRT I can put p2 b2, well I can put nRT. So w equal to nr, for p2 b2 I can put nRT2, and p1 b1 I can put nr t1 and gamma minus 1. So I can say w equal to nr t2 minus t1 gamma minus 1. So these expressions, so this is the expression, so this is the expressions for reversible adiabatic process. So whenever asked for reversible adiabatic process, use where n equal to number of moles and r is gas constant, value is 8.31 per joule mole Kelvin inverse mole Kelvin, sorry. So and it is changing with temperature. So, or you can write this w equal to nr delta t gamma minus 1. This is the expressions of work for reversible adiabatic process. And if he asks for a reversible irreversible adiabatic process, so for that for irreversible process, we say that P external is constant. That we say that for irreversible process it is happening in one steps. So suddenly we are taking decreasing the pressure. So within one steps we are doing, so on that time P external is going to get constant. So for work expression, if we says P external dB, so this P external is constant for reversible process. So if P external is constant, then then we have no any problem, because P external is constant and dB, right? So if any process, if it is a irreversible process, then always use this formula, because for irreversible process P external is constant. So if P external is constant, then no problems of doing integrations, because P external is already getting constant and only dB is there. So dB is b2 minus b1. So w equal to minus P external, because P external is already constant because of irreversible process, and dB is that is B2 minus B1. So change in volume. If you get, then you can calculate the work done for irreversible process. So for irreversible process, irreversible adiabatic or irreversible isothermal, always use formula W equal to minus P external dV, because P external is constant because of irreversible process. So only change in volume. So if the volume value given, then we easily calculate the work. So this formula is always true except if it is happening in pre-vacuum. If it says that irreversible process in pre-expansion means that is happening in vacuum. Vacuum means no air. No air means P external is 0. So if P external is 0, then what work expression is minus P external dV. And if P external is 0, then 0 into 0, that is 0. So except pre-expansions, for irreversible process always use this formula, and if it's pre-expansion, then W is become 0. Okay. So we have discussed the work done for different process. Also we have discussed about of works, and also we have discussed about of heat. So previous class we have told that work and heat are mode of energy transfer, and these are path functions. But now the question is, can you distinguish work and heat? Because both are mode of energy transfer and both are path functions. Then what is the difference between work and heat? This is for just understanding the general concept that work and heat we can only differentiate in terms of surrounding, because Q is a surrounding concept. What it says, if it is the closed systems and if we are doing the work here, this is the gas, P of gas, then whatever, whenever you're doing the work, then the induced motions is always orderly, it will go in one directions. And whenever in the closed systems, if it is the P of gas, and if heat is coming from this system, then it can go here, it can go here, it can go here, it can go from any directions. But work, it go only in a one direction. So work is orderly induced to the surrounding. Or organized motions towards surrounding. Whereas for heat, it induced randomly or unorganized. Okay, so these are the first general concept how to distinguish heat and work. This is work and this is heat. So next term is internal energy. Let's discuss about internal energy. internal energy. It is represented as either E or either U. So internal energy, if you search, suppose this is a like matter, this is a matter. So if you want to say the what is the internal energy of a matter, then the energy associated with matter is called internal energy of the matter. So for internal energy, you have to suppose you want to say that for objects, what is the internal energy of that object? So to identify, to say that this is the internal energy of that object, two conditions we have to satisfy. So for determining internal energy, two conditions we have to satisfy. One is it should be done, or it should be in isolated state. It should be in isolated state. And secondly, no external, suppose internal energy of the system I can say total, you can say, or simply you can say total energy of the system is said to be the internal energy of that matter if no external field is applying on it. What it means, let me say, if a pen, or say for this pen, this is pen on the table, so this is in the table, okay. So say this pen is in on the table. So pen is on the table. So the internal energy of the pen, if you want to determine that the pen, there should be no external field applying on it. But if it is on the table, means the gravitational field of Earth is attracting towards it. That's why it is on the table. So on that case, you will not say that the internal energy of the pen is this much, because for calculating the internal energy, there should be no external field applying on it. But if the pen is on the table, on the ground, okay, so for that case, the pen is over there because gravitational of Earth is attracting towards it. That's why that is over there. So for calculating the internal energy, we should not calculate the any external field, whether it may be gravitational, whether it may be any type of external field. We should not consider it. So if you can do that, then only we are able to calculate the internal energy. So it is a very tap to calculate the internal energy, absolute value of internal energy. So calculations of absolute value of internal energy is not possible, because we have to say that no any external field should be applied, it should be isolated systems, and that cannot be possible. So we not able to calculate the internal energy, absolute value of internal energy. So we can't calculate absolute value of internal energy, that is U. But we can calculate the change in internal energy. But the change means from one place, its internal energy this much. So after doing some like changes, the how much changes happen. So we can calculate the change in internal energy. So we can calculate the change in internal energy. And we not need the absolute value also. We only need the change in internal energy. So let's say uh, if you are going to calculate the internal energy of an object, then on that object maybe like internal energy of an object is it's due to kinetic energy, because if an object is there, then in that object, if you say in a molecular level, it has molecules which are moving. So all molecules are moving, so due to the movement of molecules there will be a motions. So if the motion is there, then that is a kinetic energy, and that kinetic energy can be translational, can be vibrational, can be rotational, and in that energy can we have gravitational energy, and maybe have the electrical energy, and maybe some other energy that we don't know. So a lot of energies are there, and when you are going to calculate the change in internal energy, then what will do? So this value what I write, let me write first suppose, so U, then this is U T, and let's say this all energy I don't know, so I write U of all external energy. Then what I will do, since maximum effect of internal energy is kinetic energy, so we are mainly giving the importance to the kinetic energy. All energies are negligible. So what it says U, so U, this I take T2. So change in, so I'm going to calculate the change in internal energy. So change in internal means U2 and U1. So U T2 plus U0 minus U T1 plus U0. So whenever I'm calculating the change in internal energy, on that time all energies which are applying like gravitational, electrical, this will be cancelled with each other. So U, that is equal change in internal energy delta U equal to U T2 minus U T1. So that is U T2 minus T1. That is delta U equal to U T2 minus T1. So change in internal energy, we only mainly calculate the in terms of kinetic energy, because in kinetic energy, what it says, kinetic energy equal to half kT square. So this is the functions of temperature, because K is constant. So it is the function of temperature. That's why UT. This because kinetic energy is functions of temperature, and this UT here including translational energy, vibrational energy, and U rotational energy. That's why when you are calculating that delta U, that is for CV, on that time you are calculating that translational, rotational, vibrational, all these things we will discuss later. So delta U equal to U T2 minus T1. Okay. So for calculating the change in internal energy, what we are doing, so we have already discussed that work and heat, these are the mode of energy transfer, mode of energy transfer. So mode can be transferred only by using either Q or W. So if I say no, the first law of thermodynamics, what it says that energy neither be created nor be destroyed. That is, it can only be transferred from one form to another. So this is given by first law of thermodynamics, that is conservation of energy. That is what says the conservation of energy. So the energy can be transferred by Q or W only. So internal energy can neither be created nor destroyed. So what the first law of thermodynamics says, since energy is transferred only by these two, and this can be only transferred from one point to another point, so internal energy will come if you add this two mode of energy transfer. This is called first law of thermodynamics. What it says that energy never be created nor destroyed, it can be transferred from one form to another form, and energy can be transferred only by two ways, either Q and W. So if you add that Q and W, then we will get internal energy, because internal energy will never destroy, and it will be only transport, and transport is only by two ways, either Q and W. So if you add this value, then you will get the internal energy. So first law of thermodynamics says that delta U, that is internal energy equal to change in Q plus change in work. So if you calculate this value, then we will get the internal energy. And he says that since internal energy is depend on the matter, so it is extensive property. So internal energy is extensive property because it depends on the matter, and it is a state functions, because except Q and W, all thermodynamic properties are state functions. Okay. And another formula for calculating the internal energy is delta U equal to mCV delta T. And this is always true for ideal gas equations. This is true for all process. So whenever you ask to calculate the internal energy, you can use either this formula or you can use this formula if you know the Q and W, or you can use this formula to calculate the internal energy. And this Cb, that is molar heat capacity, is constant. So this molar heat capacity we will take constant. If not mentioned. So if not mentions, then always take Cb is constant. If it particularly says that Cb is like they say Cb equal to 3T, then on that time Cb is changing with temperature. So on that case Cb is not constant. On that case we will write this formula delta U equal to NCB delta T, because he says that Cb equal to 3T. So here delta U equal to what? And Cb equal to 3T delta T, then delta U equal to 3N T dt. So on that time you use this formula. If they from their side they mention that Cb equal to 3T, on that time you will not take Cb as constant, because they already say that Cb is dependent with temperature. So you can put this and you could do the calculations and integrations and you will get the value of delta U. But if not mentions anything, if it is not mentions, then always take the Cb as constant. If mentions, then take as they mentions. So these are the formulas for delta U. So if not given, then you can calculate either this or this. So another thing is that for ideal gas equations, for ideal gas, for isothermal and ideal gas equation, then delta U equal to 0. Why? Because it says that delta U equal to NCB delta T, means change in internal energy only depend on temperature. And if dt is 0, for isothermal means dt is 0, then delta U has to be NCB into 0. So that will going to be 0. So this is the very, very important point, because they want to make you confused that if isothermal is there, then internal energy only depend on temperature. So if the change in temperature is 0, then the delta U will be 0. Or if Cb is 0, then also 0. Okay, so if this is the for isothermal and ideal gas equations, calculate the delta U, then delta has to be 0, because isothermal means dt is 0, and if dt is 0, isothermal means dt is 0 or T equal to constant. So T constant, then dt equals 0, then if dt is 0, then put the value, then delta is going to be 0. So these things you have to remember. So for internal energy, three things you have to remember, that is delta equal to delta Q plus delta W, and delta equal to NCB delta T, and Cb you will take always constant. If until and unless it has mentioned that Cb is this, then if it is depend on temperature, then only you can take Cb as not constant and you can do integrations. And if it asks for isothermal and ideal gas equation, then delta U is always 0. Okay, thank you.